Now I would like to introduce you to Dr. Reinhard from Johnson & Johnson Ethicon. He's the Associate Director for Research and Development, and he's the head of the plastic surgery, so please welcome him.
Hi, good morning, everybody. Thank you very much for inviting me. As a matter of fact, I received a call, I think a week ago, from my dear friend and colleague John, if I would be interested to be speaker at the NJIT Research Day. And I've never done this before. I felt honored, of course. And I'm not sure, show of hands, who actually in this auditorium thinks that is actually not aware of the fact that he or she is aging. So I clearly realize that I probably felt like, oh yeah, university, that's cool. And I didn't really realize at this point that 15 to 20 years have passed by on my end, and things happened like Sapana is calling me notoriously Dr. Reinhard or Dr. Juraschek. If you're in Germany, they have a polite plural form to show that you're an acquaintance, you're not a friend, you're an old guy. That's what happens if I walk into a university there. Those are the points where I realized time moved on and things have happened. And when I got the invitation to speak here, I was thinking like, okay, apparently time has passed on. They invited you here. What can I do for you guys that is of value for you at a research day? And talking with Sapana, we decided it would be good if I tell you a little bit, because at the time when I did my studies, there was no such thing like biomedical engineering. You kind of like had to pull it together from different disciplines. But I think I kind of like was in your shoes 15 to 20 years ago, and we decided it would be a good idea if I give you just an example how things may end up on your end. Hopefully it's going to inspire you. Hopefully it's going to trigger a lot of questions. I've also been told, since I'm a speaker here, you're not supposed to interrupt me with any questions, so you have to take it for what it is, but I'm still around for the rest of the day, so I would encourage, if I'm striking something that appears of interesting for you, if you want to follow up, if there's any thoughts that come out of what I'm going to tell you, please approach me. I'm happy to talk, answer questions, and get your perspective and your view of things. So with that being said, I would like to talk with you a little bit about my educational background. I would like to talk with you a little bit about my work in research and development in one of the big medical companies here in the US and worldwide. And I would like to close my talk today with some observations or remarks from my end, which I think were observations that what I found surprising for me when I transitioned from academia to industry, because there are differences, and I think you can brace yourself for what is going to happen to you. I wasn't really braced, and I learned it the hard and painful way. So I hope this provides some kind of input and help for you. Okay. Oh, that's working. So with that being said, as you can tell from my funny name and from my funny accent, I'm not a genuine American. I'm not John Smith. I'm Reinhard Juraschek. I was born and raised in Germany. And accordingly, if you go to university or if you go to higher education school, you do that in Germany. One of the nice things is that education is still free. It's state paying. And I spent more than 10 years at the university without even paying anything for it. Imagine that here. I started studying chemistry at the University of Bonn. Bonn, it's a question I often get. Bonn, what's Bonn? Bonn is the former capital of Germany. Now it's Berlin. Okay, it's right here. And we actually have a pretty cool campus there, 40,000 students in the former castle of the Duke of Prussia. So very picturesque scenery, and it has lots of history. I'm not sure what's your knowledge on chemistry. Somebody heard about the benzene molecule, right? The delocalized orbital structure. August Kekulé was actually one of the former professors and teachers at the Bonn University in the 19th century. He was probably resting underneath one of those trees here on the lawn when he had this vision, his dream of angels dancing around in a circle, and he came up with the idea of a delocalized electron system. It actually appears to me at this point that lots of the scientists at this time got their ideas by sleeping or relaxing. If you think about Newton, who was hit by an apple while he's sitting under an apple tree. And if you look into the history of Bonn University, professors were actually granted a certain amount of space on those lawns around the castle to hold little animals like goats or horses or cows. So those were also the time where, as an academic professor, you really had to worry about getting your food and getting your salary. So, with that being said, in the very same institute where August Kekulé was dreaming of angels and converted that into new molecular structures at the time, I was getting my master's degree in chemistry, decided at some point that chemistry is not really that what I was looking for. It's still to me a very heuristic science, so vitamin A looks like this, vitamin E looks like this, but why are they all vitamins? How does this all go together? And I pretty soon turned to physics because it's the more inductive science. It's probably harder to understand in the beginning, as Dr. Phillips can attest to, but once you have it, you can deduct from there and you can conquer the world by predicting and calculating certain things. My PhD accordingly then was in physics, also at Bonn University, and I worked in the area of bioanalytics, mass spectrometry, and ion optics. So I was exchanging the beaker and the chemicals for a lathe and soldering iron, and I was mostly working on high-frequency ion optics. Actually, Dr. Paul, one of the Nobel Prize winners in the 19s, was honored from the University of Bonn for his contributions to develop the ion trap, so how you can trap an ion in a vacuum by high-frequent electromagnetic fields. And after that, I was pretty much determined to make a career in academia, become a professor. I moved on to do a postdoc thesis at the University in Frankfurt, and Johann Wolfgang von Goethe University in Frankfurt, quite interesting. If they think about this, you all know Goethe or Goethe, that's probably the American way to pronounce it, as the guy who is a writer and an author and philosopher. But at the time when Johann Wolfgang von Goethe was living and doing his research, he thought that he would become famous one day as a scientist. And he was actually making some very fundamental investigations about the colors, the spectrum of light, and so on. And it turned out completely different for him. That's probably nowadays where nobody knows him for. To some extent, this is always inspiring to me because there are so many interesting things out there to learn and to look into. It would be a shame if you waste your intellectual curiosity just in, let's say, in chemistry or in physics or in literature. And unfortunately, the times are gone where one person like Johann Wolfgang von Goethe or Leonardo da Vinci could encompass the whole knowledge of humankind and just go into every area. But I think remaining open and having this flexibility, being interdisciplinary with research and thinking is a great source of personal joy and also innovation. Okay, with that being said, eventually at one point I was like, okay, academia is not really the right thing for me. I was doing elaborate research on ion traps, on time-of-flight mass spectrometer. I could talk to a few people in the world about what I was doing, but I was not able to explain my mother what I was actually earning my money with, and I decided to go into industry, and I joined the company Braun. Braun are the ones with the electric shavers. In Frankfurt, they were looking for a scientist with a broad scientific background, and the broad kind of like spoke to me. And from working on sophisticated ion traps and high voltage electronics, I basically switched to shavers, something as profane as an electric shaver. One thing you see here is actually the first electric shaver with which came along with a washing machine. So this thing had a display and told you, when it's time to clean it, you would stick it all over into this shaver washer and it would clean everything for you. It's kind of like yawn at this point, but at the time that we were all very excited to work on this on this shaving device. And this little picture down here is actually me before I had plastic surgery. From there, I worked in hair growth management. And believe it or not, I think that's actually one of my beliefs. If you really want to do research in an area, it's more than just a cerebral activity. How do you really find and invent something new? I think you have to feel to a certain extent. Maybe that's my chemistry background, but you have to get this transcendental feeling about what could be new and what could be different. So if you talk about hair growth management, if you talk about hair removal, silky legs, well, of course you have to epilate your legs yourself. And the ladies in the auditorium will probably give me a tip to the head or not, like, yeah, that's right. You guys will probably go like, ooh, but I can reassure you it hurts. It hurts a lot if you have one of those tweezer drums running up and down your legs. Consequently, the research in hair growth management for me was very much in the area of pain suppression. And we were trying to adopt a transepidermal nervous stimulation system, TENS, where you use electrical current to suppress the transmittance of neurological signals on your spinal cords, where you basically have the neurons, which are something like a switchboard for pain reception. We're trying to trick those neurons. And it was a very, very interesting project, very interesting time for me, where I basically started becoming very excited about medicine, about anatomy, about the human body, which, with all the respect, is much more complex and fascinating than a refrigerator or Sputnik or whatever is out there. So I kind of like widened my view at this point to the medical and biological sciences. Just to close the story, we were actually at the point where we developed an epilator, which unfortunately had to work with 3,000 volts and more, which was suspicious for our upper management at this time for a consumer product. But the interesting thing was, in panel test, you would flick a switch and you would reduce the pain perception tremendously. And that was a fascinating research to do. It never turned into a product, unfortunately. So we all, the ladies and I, will still sit there like, ouch, when we epilate our legs. Okay, but from there on, the damage was done. I was more interested into the human body, into anatomy, than I was really still interested in the high voltage electronics and physics. And when Johnson & Johnson was posting a position in Hamburg for a scientist who would have the task to build a research center for obstetric and gynecological surgery in Europe, I didn't really have to think twice. So I called, I said, I'm your guy, I have no clue about medical devices, but anything else is good. And to much of my surprise, they hired me, and that's how my career in medical devices and within Johnson & Johnson began. So as I mentioned to you briefly before, I started in obstetrics and gynecology, and I was starting in a division of Johnson & Johnson, which, if there are doctors here in the house, typically know Ethicon is the company which is producing sutures and bioabsorbable polymers, of which you can make sutures and meshes. And one of their products at the time was an invention from a European surgeon, Ulf Olmsten, who invented a thin mesh sling that, if it was placed underneath the female urethra, it could prevent stress urinary incontinence. So I'm looking into a lot of empty faces right now. Stress urinary incontinence is not a problem for you, thanks God, that's good. But it's actually for many women out there in the world, it is a big problem, and it's basically the involuntarily leaking of urine if you're coughing, if you're straining, if you put your abdomen under pressure. The next time you go shopping, just go into the aisle for feminine sanitary products and you see all the pads. So you see there's a huge market, it's out there, nobody's speaking about it. And with this treatment where you basically create a mechanical support under the urethra and help it kinking and closing shut while you're increasing your abdominal pressure, while you're coughing, there was a very convenient and elegant surgical solution created to a problem which before then could only be addressed by an extensive surgical intervention. So that's an area of research where we worked in with the team for a couple of years, and I moved on inside of the company of Ethicon, always in the role of leading discovery teams. So discovery for us in the industry really means new markets, new opportunities. Where else can we use our products? Where are other unmet needs of patients and doctors that we could answer, and where we can innovate to find those solutions? In the search of new markets, we were very quickly zooming in on, well, maybe I should just point to this picture here as well. The other area where Ethicon was known for and still is known for is, if you look at those absorbable sutures, you can weave them into textile constructions. You can generate meshes, and those meshes can help to support soft tissue, sagging soft tissue. If you think about this, the sagging urethra here is one example where you have a mesh sling which keeps it in place. The other application is in hernia. What is a hernia? Hernia is basically a weakness of the abdominal wall through which intestines basically bulge through. That's not nice. You can push them back. That's not a real good solution. The state-of-the-art surgical solution nowadays is you open the hernial sac and you implant a mesh in there, a mesh which basically reinforces your abdominal wall. So if you're looking at the technology, we were already in the area where we were dealing with soft tissue repair, and we were looking into utilizing absorbable biopolymer textile constructions to do so. So to us, it was a natural thought to actually treat another area where you have soft tissue, and that was basically in the area of plastic surgery, because if you look at it, as we're getting older, gravity takes its toll. Soft tissue is becoming lax and weak and are sagging at different parts of the body. So why wouldn't we apply the same technologies that we had readily available in this area? Something which appeared very lucrative for us at the time, and probably still is. If you look at the age pyramid, we're all getting older. And if you're looking at a baby boomer generation, where we also have enough money to spend on those things. If you look also into the area of reimbursement, while typically a hernia or a stress urinary incontinence treatment is something which is necessary surgery and is reimbursed by health insurances, typically plastic reconstructive procedures are voluntarily and elective, and people pay out of pocket for it. So that's another interesting market opportunity for a big company. So long talk, we basically focused very much into plastic surgery and facial rejuvenation. I'll talk a little bit about that in a few minutes, that you get an idea of the engineering behind those. And when then finally Johnson & Johnson decided to start a research center specifically for plastic and reconstructive surgery here in the US, they at this time probably didn't find anybody better or anybody else than me inside of the company. And we just bought a house in Hamburg. We're ready to settle, but my arm was twisted and I was transferred over here to the US. And what can I tell you? The weather is nice, people are friendly. I also think it's a more open and embracing environment for science and engineering. It probably goes back to the 60s, you are right. So it's at least my observation as well, coming here from Germany. There is more reverence, more gratitude, and more celebration around science and engineering than I'm used to it from my home country. I mean, I got my Ph.D. diploma mailed to me via regular mail, and if I'm just putting this into relation to the kindergarten graduation of my son here, where those little guys are running around with gowns and hats, I was like, wow, I didn't even have that for my PhD. So I think you find yourself here in a more appreciative culture, I would say, for those disciplines. So that's another reason why I ultimately decided to rather continue working here than going back to Germany. Okay, so that's my short biography. Let's carry on to Johnson & Johnson and the research. I think the one thing that you should probably take away is that J&J is quite a big company. We have 110,000 associates worldwide. We're making $40 billion of revenue yearly. That's about $1 million every 5 minutes. It's quite a big company, and it's divided into 3 segments. One of them is the consumer business. Many of you know, or probably it has been all on your butts at some point, Johnson & Johnson baby powder, no-tear baby shampoo. Then there's the pharmaceutical sector, and then there is an area of Johnson & Johnson which is called medical devices and diagnostics. Now, if you're zooming into this sector, medical devices and diagnostics, that's where I'm working, that's where we are working. John had been working in the past. Then there are different companies, different small companies, which are all belonging to the Johnson & Johnson empire. So the philosophy is small company environment and big company impact, which is also creating a lot of chaos, but that's another story. But you may come across some of those companies, and some of you may know. So Ethicon, we talked about producing sutures, meshes, but also more advanced things where we're using clotting factors and biologic materials to prevent hemostasis, to stop blood flow in the organism. Then there's the company Cordis, which is producing stents, drug-eluting stents. Stent procedures clearly have revolutionized the way cardiac surgery or cardiac treatments have been approached. We have Synthes, which is, you can see here, providing all kind of diffuse Synthes, providing all kind of orthopedic materials. Ethicon endosurgery, endoscopic surgery. Not sure how much you know about surgery, but you can either have an open surgery, cut the patient open, or you do everything through little incisions, through keyholes with a camera. And of course, that's lesser invasive, quicker return to work, lower risk for the patient. So Ethicon endosurgery is basically providing all those instruments for those keyhole surgical procedures. And then, interestingly enough, we also have contact lenses, Vistacon. I always think that that's a consumer product, but since it is something which changes the physiology and the way the human body works, it's considered a medical device and a medical product and falls under this umbrella. So if we're innovating, or when we're innovating in industry, or at least in Johnson & Johnson, one of the big mantras that probably John and I can sing a lot is the idea of disruptive innovation. And we have actually talked a little bit, Dr. Phillips has talked about a little bit about disruptions already beforehand. Not sure how familiar you all are with the term of disruptive innovation. I can really recommend this book here of Clayton Christensen about disruptive innovation. The general idea is that there's only a certain performance level that a customer can utilize or absorb, that you can reasonably use, that it makes sense for you. And at every technology you're looking, if you have a mature technology, then this technology advances and eventually reaches the point where it becomes an overkill, where it offers more to you than you really need and you really use for a certain application. And the art of producing interesting products and transforming products and innovation that really is meaningful is to look for disruptive innovations and disruptive technologies which at the time where you look at them may be laughed at and may not be on par with this established technology, but as those technologies develop and mature, they actually reach the point where they are of good use for the customer and meet the bill and basically, lead to a situation where this established technology is retiring. A very good example for this is we have been talking about semiconductors. A very good example, for instance, is the invention and use of transistors. If you're just thinking about, the degree of, where's my iPhone? Here we go. If you're just thinking about the degree of circuits, of logical circuits within this thing here nowadays, and if you're trying to think about how each of the circuits is a miniaturized array of transistors on a little chip, and if you then think about that each of those single transistors on these arrays would have to be replaced by an electron tube about this size, which has to be heated, that you can direct an electron beam according to the logical inputs that you're getting there. I haven't done the math, but I would probably predict that an electron tube equivalent to what I'm holding in my pocket here would probably easily fill this whole room, if not the whole campus, set aside the energy that it would use and need. So clearly, the way that the transistor technology has evolved here has reached a point where it easily satisfies my needs. Potentially this phone is even more intelligent than I am and has many more functions that I could ever use, as my kids usually make me painful aware of when they're playing with it. But that's a good example. Now, at the time when the transistor was here, people were laughing at it, and transistors and electron tubes were typically used for sound amplification. So we had tube amplifiers, people were listening to high fidelity music at their homes, and they were using tube amplifiers. So Sony is one of those companies who used at first transistors in audio equipment at a time where transistor sound was tinny, not up to par, and nobody was really interested. It wasn't really a competitor for tube amplifiers, but they tried to turn the shortcomings into a virtue. They were using the low power consumption of a transistor, the small space, as an advantage. They said, well, you know, maybe people want to have transistor radios, something which is portable, can be battery powered, can be taken with them to the beach, where, well, at the beach sound quality doesn't matter. So they found this area where this lower technology made sense and could mature over time until where we are right now, where, you know, you typically will buy a transistor amplifier even if for the high fidelity applications. So the technology had time to mature and eventually reaches this turning point where it really transforms what is used out there. So another example, of course, is the stent, as we were talking about this before. If you have cardiac surgery, if you need to get bypass surgery, not sure who of you is familiar with this, but in the good old times, you basically had to stop the heart. You have to bypass your blood flow through an artificial heart, and the surgeons would do their job. They would harvest grafts from your legs or somewhere else and construct a bypass. And then until today, it's still a very nerve-wracking job to be a cardiac surgeon, because despite of all the technologies and drugs we're having, there's still this thrill when you turn things back on. Will the heart start beating again? And as far as I understand, the chance is kind of like 1%, 1 to 100, that it won't really work. So doing all of this just to open a blocked artery, you know, you think twice before you're taking this risk. So when at first the idea was born that I just introduce with an endoscope a small metal cage which then expands and removes the blockage, it was laughed at, and it was not really considered a technology to be used by cardiac surgeons, because everybody who would run a catheter lab could do it. But over the time, it slowly evolved to a point where it became more and more reliable, and where drug-eluting stents, for instance, prevented recalcification of those stents. And now the standard of care is clearly that you get several stents before somebody would undertake the risk of undergoing bypass surgery. So that's a medical example. There are many, many others, but that's the holy grail, the thing we were looking for. Now, looking in the area of facial rejuvenation and facelift surgery, if you ever have the chance to see a video or spend time in UR, it's a pretty bloody mess. What you're doing is that you're dissecting the upper layer from your skin from your lower layers. There's the so-called SMES, the submuscular aponeurotic tissue. So you're dissecting those layers, you're pulling the tissue layer underneath it back, and then you loosely put the tissue on top of it, cut the excess skin, suture it all together. Takes about 3 to 4 hours, costs a lot of money, and you look as if you had a pretty bad car accident afterwards for at least 4 to 6 weeks. So the idea was, could we find a minimally invasive version of basically pulling back the skin in this area? And the idea was to use the, where's our laser pointer? Oh, here we go. The idea was to use the same mesh materials that would normally keep the urethra in place, or that would help stiffening your abdominal wall, to connect mobile and immobile zones in your face. If you just start playing with your face a little bit, if you try to move this area here, this is tightly adhered to the underlying bony structure, whereas this here is mobile. That's actually the whole disaster. This area is sagging down, this stays in place. So why wouldn't we connect with little anchors this area with that area underneath the skin and create a lifting effect? That was the whole idea. And a whole myriad of biomechanical research started on our end. Very interesting. To much of my surprise, we're sending rockets to the moon, we're planning a Mars mission, but if you're going into the literature and try just to find simple things like what is the force if I'm making a puckering motion here with my lips, what is the forces in those areas? The best thing we found was a loosey-goosey article from 1956, and that was it. Nobody else was really looking into the most obvious things of human nature any longer. Probably because it's not so interesting and not so prestigious, but it was of a fundamental importance for us to understand and to develop a device like this, because when we were at the point that we wanted to implant it into a patient, we wanted to be sure that it's working, that it's anchoring well, that it's growing well in, that there's no scar formation. And the other dilemma that we had is that there was no real well-established animal model for facial human aging. You can imagine, because that's an aesthetic thing which you're measuring here, you cannot really evaluate this on a pig or even on a primate or on a rat or on a rabbit. So we actually took a comparatively high risk and had to rely heavily on biomechanical testing and simulations to predict aesthetic outcomes of this very specific implant. And looking back into my research, all of my research that I've done in industry so far, this was the most interesting and exciting time, because we were really pioneering in something which you would consider obvious, faces in the face. But at the same time, we didn't find any prevailing literature. We had to do most of our measurements ourselves. We had to develop our own measurement rigs, which we were able to transport into the cadaver labs, where we were measuring forces, tissue displacement at the same time, just to create the design input. What are the holding forces that an anchoring system like this would have to hold? And what would be the elastical and flexibility parameters of a mesh implant that we would use at this time in order for it to mimic the healthy surrounding skin? You don't want to have a rigid bar sticking in your face afterwards. This whole thing must not be noticeable after implantation. So it was a very interesting time, and I think it's probably would have been interesting for many of you in a bioengineering and biomedical discipline, the whole area of soft tissue biomechanics, which if you look into biomechanics, it's typically orthopedics, because it's very well defined where the angle are. This is a bone, nothing is moving. If you're going into soft tissue biomechanics, it's kind of like comparable. You don't really find too many research and you don't find too many publications in this area, because it's so complicated, because everything is moving, it's giving over time, and at the same time a very, very interesting area of research. We actually ended up working together with the University in Zurich, developing a whole FEM model of a human face, which we could have aging over time on the computer, where we could implant our implants at different locations with different mechanical parameters, and then we're able to predict how aging would slow down, how you would reverse it, how it would continue after the implant was in place, and that helped us to design it. Of course, the most important element of that was verifying the model. So this model was designed exactly after one student they had there, Giuseppe, and we were conducting experiments on him where we were measuring displacement and forces, muscular forces at certain times, and we were overlaying those mechanical characteristics in his face to his computer version. So this whole system was more or less tailored to his face, but we were comparatively sure that what we were simulating on this model electronically would really represent reality. So all of this led to a pretty nice product, which also made it to clinical trial in Europe through a successful clinical trial. And you may probably want to ask me right now and look at me like, okay, where is it? Where can we buy it? And here we come to another interesting corporate reality, and that is the way research is done when it is done for the sake of being lucrative and making some kind of business sense at the end of the day. So I'm not sure if that's part of your studies as well and how we're developing products, but typically when you're trying to manage innovation in a company with the ultimate goal that this company is developing lucrative goals, you typically have something like this, which is called a pipeline approach. You have an innovation pipeline or a product pipeline, and you have products at certain stages here. They mature from just an unmet need in the market to a strategy, an opportunity, a concept, an exploratory phase where you explore certain concepts, where you have something like a prototype and look if it's working, yes or no. You go into a so-called discovery phase where you go deeper down the rabbit hole, where you have, let's say, 1 or 2 different concepts left, where you're testing them in model settings, where you are developing financial models for this, where you try to predict how much revenue could you make for this, do we have a market, and you ultimately end up in a situation where you have it's basically like a contract with upper management, where you're selling your soul, where you're going in front of the company's board and say, okay, you give me $3 million, you give me 10 associates, you give me 3 years, and I'm going to promise you that I'm going to develop a product like this, which will sell so-and-so many $1 million in the first year, blah, 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 and so-and-so $1 million in year 10. So you basically make this business model, and that's the big point where the decision is made, are we developing something like this, yes or no? Now with this facial lifting approach, we got approval to develop it. We actually got approval to run it through a clinical trial with the caveat, which we also made very clear to the board at this time, that this was a very high-risk project because we wouldn't ultimately know the aesthetic outcome. The aesthetic outcome, how much were patients really satisfied with a procedure like this, would be something which only a patient would be able to judge and to justify after he had this device implanted. And basically, to cut a long story short, the patients were in a 60 to 70% happy with this product. So 60 to 70% looking at different areas were happy with the outcome and would do it again. But for a company like Johnson & Johnson, and not a cheap garage company, that was not an acceptable outcome for a clinical trial. So we moved on to something else going forward. The lesson to be learned here for you going forward, and you have seen this in your research already right now, but if you're going into industry, you should really brace yourself to have thick skin. If you're looking at one of those innovation pipelines here, running an innovation center myself in Europe for quite a while, I can tell you that the ratio you're looking at is definitely not smaller than 100 to 1. That means you're looking into 100 ideas or 100 potential ideas that a surgeon is coming to bring to you. Reality is that you, at max, will get one of them through this innovation pipeline, go through this due diligence of investigating the financial lucrativeness, a reimbursement strategy, a regulatory approval strategy, and so on, and are still convinced that you make money and still make it to the market. This probability is very, very slow. So if you're working as a researcher, not only in industry, but especially in industry, you have to have this thick skin and playing different opportunities at the same time, have a plan B, C, D, blah, 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 going through all the letters of the alphabet is essential to produce something, a well-oiled innovation machine, because you don't want to bet anything on a few horses here. Now, so be prepared for this, from everything so wonderful to Super Mario hammering your thing down the drain. It's only a heartbeat away, and you get a pat from your CEO on your shoulder where they say, well, you know, the pioneers get the arrows, the settler get the land. That's how things can also turn. If you, depending on your appetite and depending on your level of frustration tolerance, you may really choose where you want to work in going forward, because typically if you look at this whole product development cycle from an idea to a ready product, it is comparatively short in consumer industry. Round about 6 months is a good estimate. If you're looking in medical devices industry, you're typically talking 2 to 3 to 4 years from the beginning of such a project to the end. If you go into pharmaceuticals, 10 years is absolutely not an exception, it's more the rule. So I think if you have some kind of awareness on your end about how patient you are with innovation and working towards a goal, that should help you to make a decision which area you want to prioritize. All right, quick time check, how we're doing on time here. Should I, okay, keep going, okay. When I was talking with Sapana about my presentation, she also was very enamored with the Johnson & Johnson credo, so I want to talk about this for a few minutes with you. One thing why I'm comparatively proud and happy to work with J&J as an employer is that next to the fact that it's a big company and a successful company and a diverse company and an international company, it has a somewhat unique philosophy. And this unique philosophy is basically crystallized in our credo. And we won't read through this whole thing, but what you can basically see is that the first thing that is listed in our credo is the needs of our patients, doctors, and nurses. So our customers come first, and then at the very, very bottom, at the end, you see money, you see our shareholders, you see fair return. So the Johnson & Johnson philosophy, and bear in mind, at the time when this credo was written, this was 1940. It sounds like a given nowadays, but at the time, that was revolutionary. Our whole philosophy is we're going to do what's right. We're going to do what's right first. And when we continue to make decisions as leaders, as employees, as human beings working in this company, if we continue to doing what's right, rather than taking a shortcut, trying to do, let's make $1 million here, let's sell this thing with 70% happiness. If we continue to do what's right, we will eventually end here that we have a flourishing company and will also, give our shareholders their fair return. So far, this worked out very well, and I have to say, it fills me with some pride to be able in working in a company like this. The biggest example of J&J applying this credo in practice was the Tylenol crisis in 1980. Probably nobody of you in the room here knows about this. I was playing with my Legos somewhere in Germany, but the interesting story back then was that some guy was managing to replace some of the Tylenol pills which were out there on the shelves in the Chicago area with potassium cyanide. So potassium cyanide, of course, highly deadly, and it ever so happened that there was a series of unexplained death in the Chicago area. And after a while, it kind of like turned out that there was a connection between those victims having taken Tylenol and, apparently with this medication. So the person who was actually doing this was after money. Here's a transcript of the letter to J&J. And the former company group chairman at this time, Burke, did the very right thing. And he said, we're going to do what's right at this point. We're not going to pay $1 million. We're not going to let this go away. I mean, take this into perspective. At this time, billions of Tylenol pills were sold, and there were 5 cases. So you could easily, at this point, and this was one of the major revenue maker for this company, you could have easily said at this point, this is not related to our pills, something else must have been happened, blame somebody else, we're not responsible for this. You could have easily kept this machinery running at this point, but J&J did quite the opposite and did what was considered by many people as a disaster at the time. They went out to the press immediately, said, don't stop using our Tylenol. Something must be wrong with this. We're not sure, but to be on the safe side, we are pulling it back from the market. And even further, we're going to replace everything that you're having at home in your cupboard at our cost with new Tylenol. because it turned out that it were those capsules that were under suspicion, but not the readily made pills. So to cut a long story short, something which was considered as a potential disaster in the end for Johnson & Johnson turned into a big turnaround. It really helped to build the reputation of a company which is doing what's right first, and it actually turned out into, along the lines of the credo, into a better trust, reputation, and better business for J&J at the end. Okay, one very tangible thing, I mean, this is all high up in the sky, but what does it mean for me as an employee at Johnson & Johnson? I think the most tangible thing for me is I'm working in a company who's really supporting social engagement and to do the right things. One thing that I'm doing, if you're working in facial plastic surgery, you see a lot of unnecessary intervention, and you're really asking yourself, what am I doing here? How do I really help patients? So I found a very satisfying outlet for me where I'm supporting humanitarian missions in underprivileged countries in cleft lip surgery and cleft palate surgery. I'm supporting those as a volunteer, as a non-medical volunteer, but also by directing company funds into the direction of those missions. And actually, as a matter of fact, Johnson & Johnson has a policy that if you do voluntarily humanitarian work, you actually get 1 week paid leave for just doing those things. And actually, I think I find this quite remarkable. This is just one example of how they're taking their social responsibility to patients and nurses out there very serious. Okay, let's switch gears a little bit, and I guess I'm the only thing that keeps you away from lunch. After talking about corporate research and the work as a biomedical, kind of like biomedical engineers, I wanted to talk to you a little bit about what to expect from moving into industry. What is going to happen? I have to tell you that at least from my perspective, I bumped my head several times, and there were things that were different than what I was used to in academia. Maybe German academia is a little bit more isolated than the environment you're working in here. There's way more internship. There are days like this where you have speakers from industry which provide you a different perspective. But frankly, when I was starting my job in industry, I mean, it was a cultural shock for me. And along to this African proverb here, yeah, I was ready to burn down the village. I was, my supervisor was an idiot. He didn't know what he was talking about. I was right. So I think I was probably pretty much a hothead to handle at this point. Actually, I met him many, many years afterwards at another conference, and I formally apologized. I said, I really, looking back, I have to apologize. I admire the patience you had with me. He just smirked. So there were at least some learnings on my end. Maybe this is helpful for you. I don't know. You let me know later, okay? So I think the biggest takeaway for me from learning in industry is really this sentence here. My work in academia was, you find teams, you work together with folks learning with something, but we typically group with the ones that you like, right? Some of you are your friends and some of them are not friends. So you kind of like meet people or group with people that you like working with. You kind of like have the same style, the same philosophy, and that's your understanding of teamwork or working together at the team. At the same time, all you're drilled towards is getting those exams done, getting certain grades, writing examinations. So all you're really focusing is the what. Do I know this? Yes or no? Am I intelligent? Yes or no? And the whole grading system is really on the what. Somebody wrote his thesis better, investigated something faster than the other one. That's your only scale towards you're looking at least I was looking at. Now, if you're coming into industry, it's a whole different ballgame. Typically, what you have learned in academia is an overkill for what kind of problems you're solving. I mean, put this into relation. I'm working at the Institute of the Nobel Prize winners for ion traps on high-frequency ion optics. And what am I going to do now? I'm developing an electrical shaver. This is profane, right? And it's easy to be toffee-nosed and arrogant at this point. And I'll come back to this at a later point again. I really encourage you to stay open-minded because you find the beauty of science and the beauty of discovering things in profane things like electrical shavers. Actually, when we did job interviews at Braun, we drove it to the extreme. If there's an engineer we were hiring, we said, well, so you're an engineer, you can construct things. Yes, sir. Okay, well, then let's construct the world's best ashtray. Ashtray, well, I was a particle physicist, I was working at so and said, yeah, we understand, but here, we're going to do an ashtray. So it was actually a very nice, interesting exercise to see if you felt that you had to work on a space mission and that would be your only fulfillment, or if you indeed would have the guts and the interest to look into a completely different direction and make it interesting. So that's the first learning, and as I progressed in industry to where I'm now, I'm a director. Director means you direct. It means I'm not soldering anything myself any longer. I'm directing people who are working as engineers. I'm managing engineers, and I'm reaching the point now I'm not only managing engineers, but I'm managing managers who managing engineers. As you're going along this typical progression of career in industry, the how becomes more and more and more important, as you can easily manage. I mean, if I'm a jerk, and if I'm treating my managers like jerk, they will treat their associates a jerk. And there's a German proverb, not sure if you have it here in the US, but the fish is stinking from the head. So it's going down, it spoils a whole organization. So if you are trying to make a career and going upward in an organization, this how you treat people, what are your values, how do you encourage somebody to do something, how do you call somebody out on some things which are not right, becomes more and more important. And at least from my point of view, it's nothing I really learned during my studies. I hope you learn it here. If not, I highly encourage you to reflect on those things and emphasize it going forward into your industrial careers. The other important thing is the teamwork, which is not only interdisciplinary. I mean, when we're working together, it's typically between surgeons, engineers, pure scientists, marketeers, and then of course our customers are in the mix. That's something I cannot stress highly enough. And of course the cross-cultural aspects if you're working in a worldwide company. It's probably not so big a shock for you here, because here in US I mean, raise hands here. Who of you guys here has been born in the US? See, I mean, we're all from somewhere else, so we're all on some level already cross-cultural. It's easier here to create that awareness and work with it. But coming from Germany, which is, kind of like a monoculture in several aspects, it was really interesting to me. And it's one of the things that makes my job still today very interesting and very challenging at the same time to get things going, to get people behind you in different technical and cultural environments. One thing I want to point out for you, if you feel that the managerial track, like manage yourself first well, then manage your project, then manage associate, manage managers, is not really appealing to you, if you rather feel that your heart is pounding for science, don't be distraught, that's okay. What we typically also have in industry is not only a managerial career track, but also a technical career track. You can easily earn much more money than I do if you just stay in a technical career, but that doesn't really mean to you that you don't need to care about the how. But even if you work in a purely technical area, it's still important that not only you're brilliant, but that you will be heard when you speak, and people just don't disqualify you as a jerk. Okay. The other second thing I wanted to make you aware of is the whole mess of a matrix organization. I'm not really sure if that's something you've been exposed to so far. I think, at least from what I've seen at academia, it's quite linear. Your assistant is always right. If he's not always right, the professor is right. So it's a very hierarchical structure. What you find in many industries and many companies is a so-called matrix organization. This is here from a different company, of course, but you have a vice president for manufacturing, for marketing, for finance, for manufacturing services. So if you transfer this to J&J, you have a vice president for for all research and development, for marketing, for customer education, for sales. And then on the other end, you go into the businesses. So you have a president for the suture business, you have a president for mesh business, you have a president for plastic surgery business, and so on. And it basically leads to a situation where, well, you have not too many Indians, but many chiefs. So you have many different chiefs, you have many different people who are making decisions and have different interests, and you find yourself in the middle of this matrix. And it can be quite confusing, because what am I supposed to do now? What is right? What is up? What is down? My only message to you at this point is you need to flip this thing around and look at it from a positive point of view. If you have many different bosses and you get contradicting different directions, it's actually stimulating something which I call an inversion of leadership. It actually gives you a lot of leeway. As long as you have a vision and an idea which is speaking to this guy and to this guy and to that guy, you can really turn the world around. I mean, look at me. You have this crazy guy from Germany who thinks about suspending people's faces with meshes, is getting all the millions for it, is kind of like failing with it, and is still making it forward in this company. Where else is this possible than in a matrix organization where you can convince and can be contagious with your passion about what you're doing and make it happen, or come to a conclusion like, you know what, it's probably not the best idea if you continue selling something like this. So if you find yourself in a situation like this later, and it's highly probable, don't be discouraged. Actually take it as an added degree of liberty that you're having. The other thing I want to point out is the importance of design control in medical devices. Do you guys learn something about design control here? Is that a topic of, you do? I get a thumbs up, okay. I have to be honest, to me that is the most boring thing I ever encountered, and I managed to stay away from it as good as possible, at least during the first 5 or 6 years of my industry career. However, it's not going on like this. We're in medical device industry, we're not just building, even if you think about the GM disaster and the ignition keys, it's not even working on consumer goods any longer. We are having a job where we have a comparatively high responsibility for people's lives and their legal and ethical considerations here to make sure that we're doing the right thing. So what you're typically doing nowadays is not really technology, what we call technology push. I have this brilliant idea, let's implement this here, there, and then all problems of humankind are solved. It's more a market pull where you start with user needs. What does our customer really need? What does a surgeon, what does a patient need? From those user needs, you define your design inputs. So what, how big, how small, how good it is. You design a process to produce a product like this, which produces outputs. So you're measuring the design inputs afterwards. You do a design verification, which basically answers the question, have I made the product right? And once this is done, you actually end up with a final medical device, which at the end, before you start selling it, you need to validate. And if you're validating something, you're not asking yourself, have I made the product right? But you're asking yourself, have I made the right product? Right? Those are two different questions. I can make something that meets my design specifications here, but it may still not help the surgeon because it's not doing what it is supposed to do to answer his unmet needs. So that's a very important element of medical devices. And fortunately or unfortunately, there is the FDA, there's the TÜV, BSI, there are legal bodies who make sure that you're doing this, and you get audited on those things. And it has far-reaching consequences if you're just, flying through there by the seat of your pants and not doing it right. You find yourself, aside from the question, would I put this into my sister or would I put this into my mother, besides of your emotional turmoil, you find yourself in trouble. So knowing about design control, honoring it, being aware of the quality systems in a regulated industry environment is a key thing, which honestly I have to say I wasn't too thrilled about. I was more the freewheeling innovator, but it's something you really have to brace yourself for and take serious. Okay, we're coming closer to lunch. Another thing I really encourage you to take away from today is this famous quote from Francis Picabia, French philosopher. One thing I see, and we talked about designing the world's best ashtray. One thing I'm observing in myself, one thing I'm observing as we're doing job interviews and hiring people. I mean, it's not a rule of thumb, but as you move on in your career and as you're learning and making your experience, it's probably a natural phenomenon that you think you know it all or you know better, and you make decisions based on experiences that you made before. On some level, you're losing this openness, your round-headedness to be open for certain things. But that is the area where if you're humble enough and say, oh, yeah, let's look into an ashtray, or let's look into this or that, that is when you're open and humble enough, that's where you find innovation and new ideas. I find myself in a situation like this right now where I'm looking into design control and life cycle management, where honestly I went into like, this is the last thing I'm doing. I'm rather going to look for a new job. But taking this step back, you actually see a way how you can innovate even there and even there help patients. So I'd really encourage you to keep this openness, which is maybe easier to maintain if you're younger and not burned that much on several things, but I encourage you to maintain this throughout your ongoing career. Okay, I would like to close my lecture with those 3 takeaways. Continue to be open and curious. Look at what you're going to do forwards as a profession rather than a job. I often get the question, what should I say during a job interview? Should I do a Ph.D. thesis? Should I do this or that? It kind of like sounds to me the wrong way around. It's like you make yourself compliant in order to get a job later. And believe me, this mentality will be soon recognized in job interviews or while you're doing your job later. If you're in it with your heart because you're excited, because it's your profession, or if you're just trying to be compliant and say the right thing so that some people get you the right money for it. So keep in mind that what you're doing, you will do for quite a while for the rest of your life, and you rather want to do something you true-heartedly enjoy, where you're really good at. The other things I encourage you on is to try things on for size, internships, questions, shadowing somebody at work. It's almost like wearing a different suit or a coat. How do I look in this? Do I feel comfortable? I hate this tie, but you know, it gives you a good idea, a good insight in how your job would later look like. I didn't have this luxury. I was in a somewhat isolated environment, and as you've seen from my biography, I developed inside of the job and inside my studies, from chemistry to physics to medical devices, into the managerial track. But the better you can try certain things up front, it helps you to tailor what you want. And then, yeah, the last point I already made before, remain open, don't end up like Waldorf and Stadler. With that being said, thank you very much for your time and attention, and I'm happy to receive any questions later.
I would like to call upon Dr. Charles J. Fay, who's our Vice President for Academic Support and Student Affairs. Let's welcome him, new face.
Thank you, Sapana. My face is hardly new. It's been on the planet for almost 65 years, so I can say it's not new. I am not going to speak very much. Number one, I'm not a scientist. Number two, I'm not an engineer. So all of you who are doing what you're doing is just so amazing to me as I sit and watch it. I thank you all. In fact, let's give our previous 2 speakers another round of applause. Thank you, Dr. Phillips and Dr. Juraschek, for being here with us today. In higher education, research has a critical role to play. It's one of the 3 primary reasons that faculty do what they do, that I do what I do in higher education. Research, teaching, and service are what we're all about. Research provides the opportunity for faculty to continue to discover new knowledge and then transmit it to people like you who will become the future researchers, the people who will begin to, will continue to change the face of our society as we go forward through the final 2/3 of the 21st century. We will progress based on what you discover and what you're able to produce for us as a society. And NJIT has a great history of providing great research and researchers for our society. You, as new researchers, as students learning about the process and discovering the things that will change our society in the future, you are following in the footsteps of many terrific researchers in the past. And I just wanted to take the opportunity today to congratulate each and every one of you for what you're doing, for the posters that are upstairs that I walked through a little while ago and looked at. And frankly, again, I'm not a scientist, I'm not an engineer, I can't spell half those words if someone asked me what they were. So I'm just in awe of what you can do and the knowledge level you have and the things that you produce. Thank you very much. I'm going to let you eat, right? Is that the next thing we're doing? You're going to get to eat lunch, and then while we're doing lunch, Dr. Atam Dewan will be doing what he was going to do next on the presentation. So while you eat, pay attention to the films as well. Thank you very much. Congratulations to every one of you.
Thank you, Dr. Fay. Now we're going to call upon Dr. Soitras Ziziaras. He's our advisor for Graduate Student Association, and he's also the Associate Provost for Graduate Studies and the Vice Chair for the Research. So let's welcome him. And he's also our father of GSA.
Welcome again. I know we are behind schedule, so I will not spend a lot of time. You need to have lunch. It is the right time for it. Basically, I will give you some statistics about graduate studies at NJIT, primarily for people who are here for the first time or they have not been at NJIT, as students. We have about 3,000 graduate students at NJIT. This is close to our all-time high of 2001. So in graduate studies, we are doing extremely well. We are producing about 60 Ph.D.s per year. That number was a few years back was about 70, for a while. But we are going to go back there. We are making some changes to increase our numbers at the Ph.D. level. We have a really great faculty. We have actually hired 50 new faculty in the last few years, and so which is a very good number out of a total of about 280 faculty members at NJIT. They are extremely active in research. They are very well known. So NJIT is in a new phase. You will see that when you go upstairs later on after lunch to look at some of the posters. They are doing outstanding research. At the same time, I can tell you, since basically a substantial part of the discussion this morning, of the presentation this morning, was related to biomedical engineering or biology. We have good ranking with respect to that. For example, students have ranked NJIT as the 10th best in the nation in terms of satisfaction at the graduate level. Chemical engineering is number 20. We are also ranked extremely well nationally with respect to basically the salaries that our graduates get. We were number 1 nationally a couple of years ago among all the universities in the United States with respect to the salaries that they get compared to the tuition they pay at NJIT. We have very good image, primarily in recent years, so things are improving a lot for NJIT. Again, I don't want to spend a lot of your time. Welcome again, and enjoy your lunch. Thank you.